Hello everyone and welcome back to this next lecture. So in the previous lecture we had written the control code for the operation of this bidirectional buck boost converter. In this lecture let us analyze the result. So this particular result corresponds to a forward buck operation. So for instance, if you come over here and have a look, the output voltage is much lower than the input voltage. So clearly we have a buck operation. Now, I will leave it to you as an exercise to interpret the gate pulses voltage, right? I will leave that to you as an exercise as I have already done it several times. I do not want to repeat it again in this lecture. Instead, I will talk about two other quantities. The first quantity is the inductor current. So as you can see, the inductor current is positive. But always whenever you see a current, it is always advisable to go and verify the direction from the schematic. So I'm just going to pull this down and come over here, and for that let us hover over one of the terminals. So you see here the current IL1 is positive, which means that the current entering the terminal is the positive current. And if you hover over this, you will see exactly the opposite. This is a minus IL1, which means the current is leaving this terminal, right? So which means that in our case, the positive direction of current is from left to right, and as you can see here, the current is positive, which means the current is indeed flowing from left to right, which means the power is flowing in the forward direction. So this confirms the fact that we are indeed working in the forward power flow direction as expected. Now let's look at this bridge voltage, which has a fairly interesting structure. So if we take a look at the bridge voltage, we will see that the blue waveform is VBRG1, which is the output of the left half bridge module, right? This is the left half bridge module, and this is a switched waveform due to the fact that this upper MOSFET here, M1, is being turned on and off. And since it is being turned on and off, whenever it is turned on, this net, that is bridge BRG1, is connected to the positive DC link voltage, and whenever it is turned off and the diode is conducting, the BRG1 is connected to the ground. And that is why you have a switched voltage, right? Let me zoom in again. On the other hand, VBRG2, which is the red line, seems to be constant. And if we take a look, it is actually constant at the output voltage, at the value of the output voltage. Now let's see what's actually happening. And the reason for that is that in both conditions, it is the same diode which is working. In the forward buck mode, the MOSFET M1 and the diode D3 are conducting. On the other hand, when the MOSFET M1 is turned on, diode D2 conducts, but diode D1 is still conducting. Therefore, in all conditions, in both conditions, BRG2 is connected to the positive DC link. And therefore, as you can see, the voltage of VBRG2 is simply the output voltage. Now, let's flip this over and run another particular example. So for example, I have seen what we did here was forward boost. Let us now change this to reverse boost, or let's change this was forward buck, sorry. Let's change it to reverse boost, just for the sake of an example. So in this case, I'm going to make this -1 because this is the input to DIR, and here we have used the convention that when it is -1, it is the power is flowing in the reverse direction. And for mode, when we put a value of -1, it means that it was in the buck mode of operation, or rather the output is less than the input. So let us change this to 1, in which case it is the boost mode of operation, where the output is greater than the input. So with this done, we can't directly run the simulation. We must provide an actual voltage. Because if we have to supply power from the output, then in that case, it is essential, let's actually make this 24. It is essential that we have an energy source on the output and we have only a capacitor as the input. So with this done, we can run the simulation. Let me just close this down so that we get a fresh result. And now you see the result is fairly different. So the first thing I'm going to do is, let me just change this to red because I don't like that color at all. Now it's clear. So first things first, let's look at the inductor current. And as you can see, the inductor current is negative, right? So therefore, very clearly, the output is supplying energy to the input. We have reverse power flow. The next question you should ask yourself is, what is the output and the input? Now the output is constant at 24 volts, and that is because we have placed a voltage source at the output which holds this output constant. But now let's take a look at what's happening with the input. The input now is 6 volts, which means that the input is lesser than the output. So we have a reverse boost mode of operation. Because when I say boost mode of operation, it means that the output is greater than the input. So here you can very clearly see that we have achieved a reverse power flow and we have achieved a boost mode of operation. So this shows the flexibility that is available with this particular converter. Now let's go and have a look at our bridge output voltages. If you take a look at the bridge output voltages, now you will see that the BRG2, which is the red waveform, is a switched waveform. And the reason for that is because in the reverse boost mode of operation, we have the device M3 conducting. Because we are now achieving, because remember, in boost mode of operation, the output is greater than the input. But since we have a reverse power flow, that is power is flowing from the output to the input, in the direction of power flow, we have actually boost mode of operation. We have buck mode of operation. Because remember, if the output is supplying energy to the input, then in that case, we are performing a buck operation because the output is greater than the input and output is supplying energy to the input. And what that means is the device M3 is intermittently operated. Either the device M3 operates and the output supplies energy to the inductor and the input, and when the device M3 stops connecting, or you can say is turned off, then in that case the diode D4 freewheels and diode D1 and D4 conduct, and the energy in the inductor is supplied to the input. So therefore, if you take a look here, you will see that the bridge 2 is a switched waveform. Because when the MOSFET M3 conducts, then BRG2 is connected to the output voltage. And when M3 stops conducting, then diode D4 will conduct and BRG2 is now connected to the ground. On the other hand, if you take a look, BRG1 is always connected to the input voltage. And the reason is because in both modes of operation, only diode D1 is conducting. And therefore BRG2 is connected to the positive DC link. And if you take a look here, that is exactly what you will get. You will see that the blue line is actually the input voltage, the same as the input voltage. So these are things I would encourage you to verify on your own. And also please verify the gate pulse voltage. I have skipped it in this example because I have done it in many other examples. So I hope you got exactly the same results, and I would suggest also, as an example, try out the other two cases. We tried forward buck mode and we tried reverse boost mode. Try out the other two modes as well, that is forward boost mode and reverse buck mode. These are things I will leave to you as an example, as an exercise. So, if any of this was not clear to you, or you faced any other issues, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much for listening and goodbye for now.